Okay, so last class we had so Yiming discussed the polynomial method proof. And how it can imply that right. So one way to think of this bound is that it is polynomially small in the domain size, right? So if I let capital N equals 3 to the n, then this is saying that R3 of this number is less than n to the c, where c is less than, right? But over the integers, on the other hand, we know that this is at least n over 2 to the root log. Okay, so there is a substantial gap. Here, the exponent can never be better than 1, but here we already know it's like 0.7, point something. Okay. So today, what I want to talk about is the poll was very inconclusive. So what I'll do is be a benign, benevolent dictator and choose both topics to some extent. So today I'll give you maybe a very high level overview of the proof over integers, that this is at most n over 2 to the log n to the omega 1. Okay. And it'll be a very high level overview. I'll skip many details. And in fact, I'm only going to talk about this in the setting of f3 to the n, but at least it will give you a sense of the main ideas that are in this new proof. Okay. And compared to the other things that we did, we will skip many, many details, because otherwise it just takes too much background and too much stuff to actually cover the proof fully. Okay. So that's the idea for today. And the next two lectures, again, I'll go back to there's this cool new result about space efficient tree evaluation. Okay, so I'll talk about that problem. And that will kind of be our last topic. And if time permits, I'll discuss some connections between the tree evaluation problem and other things. But before I jump into any questions so far from last lecture, or what we'll cover next? Okay. All right. So today I'll just talk about kind of the high level ideas behind this, and maybe if time permits, some kind of directions for future work and connections to communication complexity again. All right. But as I said, keep in mind that this lecture is going to go at a high level. We won't go into the nitty-gritty details. But if you have any questions, you're welcome to ask me afterward if you want to follow. Okay. All right. So with that, let me do something which is all right. Okay. So let's recall the setup. I'm going to only talk about the setting of finite fields again of F3 to the n, just as we discussed in the last lecture. So we'll see a different proof, a more complicated proof, kind of a more messy proof too in some sense, which will give a worse bound. Okay, so it's going to be worse on all fronts when you think about just this question of F3 to the n. But the gain is that this technique, the new proof, can actually work or can actually be made to work over integers. Okay, so that's the benefit. So like the proof that we saw based on polynomials uses the algebraic method, right? So you have to somehow count number of free variables and do some accounting there. And it doesn't work over integers. And as we've been saying, it shouldn't work over integers because it's proving a bound which is substantially stronger than what would contradict Behrens' construction, right? The proof method is very beautiful, very clean, but we have not been able to make it work over the integers, and for good reason too, because this is Behrens' construction, okay? On the other hand, all of the other works starting from the 50s in math and combinatorics and so on have been analytic in nature. Somewhat they use Fourier methods, kind of make it work over finite fields first as a test bed, and then push the argument to integers, okay? So today I want to kind of sketch an analytic proof over finite fields that this kind of density suffices, okay? What does this mean? Any set with roughly 2 to the minus log n to the 0.11, which is like 1/9 fraction of the elements, will contain a 3-term arithmetic progression, right? As I said, this is weaker than what you saw in the last lecture, but the proof method can actually be made to work over integers. So that's the gain, all right? Okay. And in our original result also, we worked over finite fields, then kind of pushed it to integers. And subsequent to our work, in fact, within a week, Bloom and Sissac found a much cleaner way to kind of lift what we are doing to integers and also to all abelian groups. Okay. And also got some new improvements in the concept. Okay. So that's kind of what we're going to talk about. And the proof over finite fields has 3 parts, right? So again, just a reminder, we have a subset A of F3 to the n, 0, 1, 2 to the n. It has delta fraction of the elements. We want to understand at what delta are you guaranteed to have solutions to A plus B equals to C, right? And the proof kind of has 3 parts. The first part is what we call spreadness to mixing. And it uses something, an old technique in math and combinatorics and in computer science called structure versus randomness, but with a twist. And then it has to kind of, standalone ingredients, which I'll talk about, okay? And let's start with the first part, the spreadness to mixing. What does it mean? Okay. So before talking about the new argument, and we already saw one argument for the polynomial method last class, but let me go back all the way to 1950s. So how did Roth approach this problem? And the way he did it was kind of introduce this sort of win-win analysis, which we now call structure versus randomness, okay? So just imagine this is my universe, and obviously it's a caricature. And I'm denoting every point, every n-trit string as a point in this cube. And the set A is shown in yellow here. It has delta fraction of the elements, okay? And what are we trying to do? We want to say that, okay, so once this density crosses some threshold, we will get many 3-A's, right? And we did this heuristic calculation earlier. One calculation that we did earlier was, okay, what happens if the set A is chosen completely at random, right? So if we choose the set A completely at random with density delta, meaning every point is going to be colored yellow, is present in the set A with probability delta. The number of 3-A's you should see should be delta cube times capital N squared. Why? Well, each triplet ABC would be present in the set with probability delta cube because each element is being added independently. And there are roughly n squared many 3-A's. You get to pick A and B, C is fixed. So you have capital N square many 3APs. So delta cube times capital N square should be the number of 3APs you should see. And as long as this number is much more than delta times N, you'll start seeing many non-trivial 3APs. Okay. So the first wish we are going to make is that maybe this calculation doesn't need the set A to be completely uniformly at random. Okay. Maybe this argument is robust enough to apply even when the set A isn't completely random, but it's close to being uniformly random. Okay. It's close to a distribution where each element is chosen independently with probability delta. Okay, closeness we have to characterize, but maybe even if the set A is close to uniform, this calculation can be made to work and it has many 3APs. All right. Okay, so that's wish one. Obviously, if you just have this, it's not very useful because you need also some to handle the case when your set A is not close to uniform. Right. So the second wish is to somehow hope that if this hypothesis doesn't hold, that your set A is very close to uniform, then you can somehow do something else. And they do something else, we are going to hope to use induction. Okay. So this close to uniform is this. And the wish two is going to say, if I'm far from uniform, meaning I'm not close, then there is some strong structure that we can explore. Very wishful thinking, right? We are saying either you're close to uniform, barring that, you have some structure, and then I can use. There's no middle ground. That's the hope that we have. Okay. So it's kind of wish in thinking or win-win analysis. And the specific structure that we want often depends on the type of problem that you're trying to solve. Okay, so this template kind of can be used in many places. In the context of 3APs, the structure that's very useful for us is the following. Suppose I tell you that if you're not far from uniform, then there is some subspace or even an affine space V, where relatively speaking, have more elements than before. Right? So as the set A is part of F3 to the n, but we can think of F3 to the n as a subspace. It's an n-dimensional subspace. It has some density in there. I'm saying if you're not close to uniform, then I can go to a subspace or an affine space, doesn't matter, where the relative density of A, meaning A restricted to V divided by the size of V is more than delta. So I'm gaining something in the density of the set I'm working with, right? But if I go to the subspace, it's the same problem again, right? Because all subspaces are, arithmetic over subspaces is always the same. I can just do a basis change, and I'm again asking the same question. I have the set A prime, which is subset of the subspace V. Does it contain three elements A, B, C, such that A plus B equals 2C? So I'm getting the instance of the same problem, kind of a smaller size, because V could be smaller, but more importantly, the density is higher, right? As the density of the set A increases, it should be more likely that you'll find 3APs. So that's the win-win. Either my first heuristic argument works and I'm done, or I can go to a smaller thing where I have more density, more elements than before, so I can repeat. Okay, yeah? In fact, maybe inspired is a strong word, but it's definitely kind of, one way to think about it is, as you'll see, the logic is the same, right? The logic being that just do all of the increments that you want in one loop. So in that sense, it's the same, okay? I mean, major could be qualitative because it's one of my own papers, but there's a paper that we had in 2015 in communication complexity, which in fact also defines something very similar to this notion of spreadness called blockwise density of distributions. And they're also, instead of looking at one at a time, we just go all in, and then that gives you some benefit. I can tell you more about it later. Okay. Okay. So this is our wishful thinking for now. We're going to say either I'm close to uniform and the heuristic calculation in whatever form can be made to work, or I'm far from uniform and then somehow I win because I end up with a smaller instance of the same problem with more elements than before. Okay. And this is how kind of, the 1950s proof went. Of course, our integers things get a lot more complicated. Maybe I should say one thing. Okay, I'll say that later before I conclude. So in the first case, what does it mean? What is the analog of this close to uniform? So one way to think about closeness to uniform is, again, from a computer science perspective, right? Someone gives you a distribution and says, okay, this is actually truly random bits or truly random strings. How do you test it? I'm going to design an algorithm to try and break your pseudo-random generator. Okay? So that's what we do always. I'm going to come up with a test function, which is going to say that, okay, whatever you're generating is not truly random. There is some bias inherent in it. Okay? So the first thing that happens is that, actually a small notion of pseudo-randomness, a simple notion of pseudo-randomness is enough to make this calculation work. The heuristic calculation for counting the number of 3 And what is this notion of pseudo-randomness? It's just saying that you're claiming your set A is kind of uniformly random if I cannot tell it apart from random from linear tests. Meaning, the only way I'm going to check if you're close to random or not is add up the individual coordinates and check the result mod 3. Okay? So a set A is called, is set to fool linear tests, or in the language of error correcting codes or pseudo-randomness, it's called small bias, if the following holds. You have your string X that is generated by picking a uniformly random element from A. If it was completely random, when I add up all of the coordinates, it's going to be 0 mod 3 with probability 1/3, 1 with probability 1/3, and 2 with probability 1/3. Right? All of these values should be equally likely. Okay? And we're saying it fools linear tests with error delta if this holds, meaning every one of these probabilities is very close to 1/3. It's 1/3 plus or minus some delta over 6. Okay? So you gave me your pseudo-random generator. By adding things mod 3, I'm not able to tell it apart from truly random string. Okay, so that's where I'm stuck. So in that sense, it is pseudo-random. Okay? Any questions about this definition? Okay, so the first thing, it requires some Fourier analysis to show, but you can show that if the set is small bias, meaning it fools linear tests, then it must contain many 3APs. Right? And that covers the wish one. Closeness to uniform means that it fools linear tests. The other case, when you're far from uniform, is kind of almost immediate from the first definition. If the set is not small bias, meaning there is a linear test which is telling me apart from uniformly random string, then there must be an affine space. In fact, one where I only add one constraint and I increase the density. Okay? Why is that? Well, if the set A is not fooling linear tests, then there is some W where this number is greater than 1/3 plus delta. And that W is going to give you affine space. It's saying if I restrict there, I have more elements than what I should have. And you work through that, you get this. Okay. In some sense, in this dichotomy, part 1 is the harder part. Part 2 follows from the definition. Okay. Usually one of these things will be somewhat easier than the other, but it's just like, in this case, this is the situation. So what do I do after this? So I started out with the set A, and the universe is all possible n-th strings and density delta. If I am fooling linear tests, then I'm already done. I have many 3APs, I'm done. If not, and there are no 3APs, then my wish 2 kicks in, and I can find an affine space, V1. Look at the set A intersection V1, reduce to V1. But the density now is more than the density I started on. Okay. If I have many 3APs, good, I'm done. If no 3APs, once again, I can find a smaller set V2 where my relative density is even higher. And I keep repeating this. And at some point, my density becomes a constant factor more than what I started, right? And the point is that you cannot keep on increasing the density forever. The density can only be one, right? So at some point, this needs to stop. And if you set up the parameters properly, you'll get some contradiction and some quantitative one. Okay? So you can't increase the density forever, so you should get some contradiction. And you follow with these calculations, you get that any set A, which has at least 3 to the n divided by little n many elements, must contain many 3APs. And you can clearly see this is much worse than what you saw last lecture. In fact, exponentially worse. And this is like, if you, in terms of domain size, it's like capital N divided by log of capital. Okay. So you follow this approach. This is basically Roth-Mechoulam argument. It gives you like 1 over log density sets must contain 3APs only over finite. Okay. All right. So let's say I want to go beyond this for, again, over F3 to n. Using the same approach, I want to get better quantitative bounds. So what do I do in that case? And we can roughly think of this as being split into 2 steps, right? We need a pseudo-random argument to say, even if my set A is pseudo-random or close to uniform, I get many 3APs. That's kind of the wish 1 part. Wish 2 is to say, if I'm far from uniform, then I want to find a subspace with more elements than before. Okay? Quantitatively, what matters is this dichotomy. Like, when I say far from uniform, how much of a boost do I get in density? Okay. So in the previous case, we're getting a tiny boost, like in delta plus delta squared kind of boost. But if you get a bigger boost by going to, even a larger subspace, then it's better. Okay. And this is called density increment part. You're saying I can go to a smaller set where I have more elements, so my density has increased. Okay, so let's talk about the second step. I said in the old sort of Roth argument, the first step was the hard part, and the second step was kind of easy, kind of follow from the definition. And we're going to do something similar again by pushing all of the difficulty into the first step, right? Meaning I'm actually just going to define the second issue away. Okay, I'm going to throw it under the definition bus. Okay. So what do I mean? So just think of the statement. What are we saying? That if I'm far from uniform, then there is a subspace with more elements than before. So I don't want this to happen. What do? I'm just going to look at the contrapositive and make it my definition of being close to uniform. Okay. So I'm going to say I'm close to uniform if there is no subspace under which I have more elements than before. I've just made it tautology. Okay. But then the first step will become hard. But there's a conceptual boost that you get here because, in some sense, you're not going one dimension at a time. And you don't have to find the subspace in some sense. Okay. So this leads to this notion of spreadness. Okay. Spreadness just says that I cannot do induction anymore. So this should remind us of what happens in sunflower, right? So in sunflower also, spreadness basically said that, somehow I can't go to a link and I'm not getting an increase, right? So meaning induction is not going to work anymore. In every link, I'm in the same situation or worse than before, so I cannot use induction, okay? This is exact same thing. I want to say that I cannot use induction at all, right? Or I'm at a stage where I cannot use induction. I have to work from first principles somehow. At what stage can I not use induction? Well, you have the starting set A, subset of F3 to the n. if there is a big subspace where I have more elements than before, I should be going there and use induction. Okay, and this is saying there is no such subspace. So for every subspace which has codimension D, so you measure largeness of a subspace by how many extra constraints you have, because these subspaces are going to be very big. Okay, so if I add one constraint, I lose roughly 1/3 fraction of the elements. Okay, so I'm going to add D constraints at most. So we'll say the subspace A is D spread if for all affine subspaces V of codimension D, meaning I have at most D constraints, the density of A restricted to that subspace is no more than a small constant fraction, constant times the overall density. Okay, so if it's 1.01 times the original density, which was delta, let's say. Okay, if this is not the case, I should just go and work in the subspace V. I have more density, and maybe I can just apply induction directly. Okay. Any questions about this definition? It's quite important. Right, so I was saying the logic is that you should make the density increment part somehow easy. Just take all the density increments that you can up front, and then what you're left with is what you're left with. Right? The same thing happens in Sunflower too. You say, okay, if you find a link, just go there. If you find a link, go there. At some point you get stuck. That's when you have to roll up your sleeves and prove stuff. Yeah. So D spread is just saying that go to any subspace with codimension D. My density is no more than 1.01 times the original density. Okay. If this is not the case, then what would I do? I would just go to the subspace 3 and use induction. I have more density there and a smaller dimension, so I can just use induction, right? So in that sense, it's similar to Sunflower. Yeah. I mean, for this, I think, we might have even used 1.01. In the actual paper, we just called it 1 plus epsilon, where epsilon is going to be set as some constant. Here, I'm making it 1.01 for simplicity. Okay. The last time I checked, someone worked out the constant and it was bad. Basically, there's a project underway to code this all up in Lean, the automated theorem verifier. And there you have to be specific about constants. And one of the constants, like 2 to the minus 100 or something. Not this one, but something else. But anyway, so we kind of defined the second thing away. But now you have to prove the first part. The first part will say, if my set is spread, meaning there is no sort of a single subspace which has a lot of elements, then I should contain many 3As. Okay. And I think spread is a good term for this definition because intuitively that's what it's saying, right? Spread means I'm kind of all over. I'm not focused on any region in space. Region here corresponds to subspace. There is no structured set like a subspace where I have more elements than I have overall. Okay. All right. So now we have to show the main thing, which is that a spread set must have many 3-term arithmetic progressions. How do we approach this? Well, so here we're going to start talking about what it means to have a 3AP a little bit more and formulate it in a slightly different language. Okay. So if you think of this condition of 3AP, what we really want is we want distinct A, B, C such that A plus B equals to C. Okay. And one thing that happens often in many of these proofs is the condition of distinctness is you kind of get it very indirectly. You just say that there are so many solutions that many of them must be distinct. We're just going to count the number of solutions really. Okay. So it's A plus B equals to C. And one equivalent way of writing this condition is like, even though it seems like there are 3 variables, there are really only 2 variables here. Once in A and B, C is fixed, right? So let me, just reformulate the same condition that way. So you want many pairs A comma B such that A plus B is in the set 2A. what is 2a is some other set, which is just, you take every element in A, multiply it with the number 2. Again, remember, this is modular mod 3 arithmetic. Okay. So whenever A plus B lies in this set, I'm happy, because that means that there is a solution where you have A, B, and C. Okay, just rewritten it in a equivalent way. Okay. Now you might ask, okay, how do I count how many pairs AB there are? What's a good way to count? I can say, okay, maybe I should really count how many pairs, the absolute number. Do I want the asymptotics, or what do I do? Okay. And it turns out that the right way to count, especially when we are trying to, when we keep changing the underlying universe, right? We're moving from one subspace to the other and so on. The right way to do this quantitative count is in the language of probability. Okay. Probability is, you can also use it to count, and that's what we're going to do. Instead of counting for the number of exact pairs A, B, such that A plus B is in the set A, it's easier to talk about, and it's equivalent nevertheless, but it's easier to talk about the probability that if I pick X independently and uniformly random over A, and Y independently and uniformly random over A, what is the chance that their sum lands in the set 2A? Okay, so X is like little a, Y is like little b, but I've just made them random variables and looking at the probability instead of counting the number of exact pairs. Okay, so up to some, like 1 over n squared term or something, these two are equivalent. Okay, and now we can just do some heuristic calculation for heuristic guess of what would be the ideal answer for this probability. Right? If A was a completely random set, that's our mental blueprint for what we would like A to behave as, right? If it was a completely random set, it has density delta, right? So then this random variable should be landing in this set A with probability delta. Okay. So we can ask, okay, can I hope for delta over 10 maybe? It might be an overkill, but if it was completely random, I get delta. Can you at least get me delta over 10? Okay. So far, it's like, we're following the definitions in sort of greedy way. And now comes some things that we can really exploit. The first thing that we can exploit is, so here we have two random variables, X and Y, which are independently drawn, and we are adding them up. Okay. Seems like a complicated operation over distributions, right? If you ask me for a distribution of X, it's easy. It's uniformly random over A. Y, it's identical, uniformly random over A. What about the distribution of X plus Y? When you add up two independent things, what's the distribution of the new random variable? So just to just as a kind of proof of concept, what I did here is, so the intuition is that X plus Y should be more random than either X or Y. When I add up two things, somehow we would expect it to be closer to uniform, right? This entropy should increase. So for instance, this blue line here, I drew some 1,000 numbers from 1 through 10,000. It's a very discrete set. Its PDF is kind of spiky, is not at all close to uniform. Okay. And the purple line is the PDF of X plus Y. Okay. And you can see once I convolve, the PDF is become like very flat, almost uniform, right? If it was exactly uniform, I would get 0.001, that is 1 over 10,000, right? But as soon as I convolve the two things, I get a distribution which is very close to uniform. So the advantage in this equation is that it's not saying, okay, show me that X is close to uniform or Y is close to uniform. It suffices to show that X plus Y is close to uniform. Okay. And in this example, for instance, the individual one is not close, but as soon as I add, as soon as I do this addition, I get something which is very close to uniform. Okay. And not only that, but probability 101, we know exactly what the density of x plus y is, right? So if the density of x is mu a, and the density of x plus y is the convolution of the two densities, mu a star mu a. Okay. If you haven't seen convolution before, it's an operation defined on, most importantly on probability distributions. Okay. And if I have two functions f and g, their convolution f star g of x is essentially you draw a random variable z, look at f of z times g of x minus. Okay. So you multiply f and g, kind of the inner product, but only on inputs which add up to x. This is the usual notion of convolution. And there is also this notion of difference convolution, where instead of looking at pairs which add up to x, you look at pairs whose difference is x. Okay. So there's the star convolution and the difference convolution. They do behave differently, but let's, in this statement at least, is just the star because we're adding up x plus. Okay. Any questions about this? All right. And I should say something about the normalization, which I haven't here. But so instead of talking about the PDF of x, I'm talking about the density of x. And is there a marker here? Okay. All right. So density is just kind of a rescaled version of the probability density function. So you might have seen PDF before. So density is just PDF scaled up so that the numbers are normalized so that they're around 1. Okay, I'll talk, so it's just as rescaling so that things become nicer numerically. Okay, so what do we need to say now? We need to say that if A is spread under a notion of spreadness, then the density mu A convolved with mu A is close to the uniform distribution. Okay, so uniform distribution, the probability density of any point would be 1 over the domain size, right? So it's difficult to carry this 1 over domain size everywhere, so you just normalize so that you don't have 1 over the domain size. Okay, so density is just like domain size times the PDF, so that we are comparing with 1 instead of 1 over n every time. Okay, this is especially useful when the underlying space keeps changing. The capital N could be like something else later on, so you're always comparing just with 1, right? So this is what we need to show, the main thing. If A is a spread set, meaning it does not contain any of these does not contain any subspace on which it has more density than earlier, then as soon as I convolve it with itself, I get the constant function, or I'm very close to the constant function. All right. And one way to think, kind of have a caricature but helpful picture in mind is just imagine on the x-axis, I have the entire universe 0, 1, 2 to the n, right? Entered strings. Now, mu a star mu a is some function on these things. It tells you what is the probability of seeing this particular point under the distribution of x plus 1. Okay. But we scaled it up so that instead of looking at very tiny numbers like 0.001, we boosted everything up so that we're comparing always with the constant 1 function. Okay. So the uniform distribution will be the constant 1 function, and our mu s star mu a could be all of it. What we would really like to say is if A is spread, then mu s star mu a is very close to constant in some metric. And the mental picture of closeness again should be, we'll define it in a second, but the qualitative thing is we really want to say that this density doesn't have too many points over here. Okay. In some sense, it's okay for us if it goes above, but we're really worried about having too many points with small probability. Okay. Because if you have too many points with small probability, because we're only interested in lower bound. I mean, we'll get both, but we really care about the lower bound. Okay. All right. And this is really the main claim. What we show is that if you have a set A which is spread, then mu A star mu A is very close to the constant one function. In particular, mu A star mu A does not have too many low probability elements. Okay? The number of things where this density is less than 0.9 is going to be very small. Okay, so technically, what we show is that if A has density 2 to the minus d and is d to the 10 spread, and the amount of spreadness you require will depend on the starting density of A, then if you look at all points and the number of points where mu A star mu A is not very close to 1, it's not within 0.9 and 1.1 is very small. Okay, so we're saying, okay, you want it to be 1 all the time. I'm not going to be able to say it's 1 all the time, but except for a tiny number of points, I'm within 1.1 and 0.9. Okay. And technically, I mean, that's the interpretation. Technically, you just work with the kth norm for k, which is very large. K is like d or something. And finally, if you have this claim proving that mu A star mu A, once you have this is close to 1, then you have many 3AP is very easy. Okay? In fact, all you need to say is that 2A is a dense set, so you cannot avoid it completely. Okay, let me summarize this part. As I said, in some sense, the main things that we did so far is to come up with a new definition of spreadness, right? And sort of the only other math that would go into is proving this claim that if mu A star mu A is close to 1, then we have many 3APs. Other than that, all of the difficulty is hidden in this claim KM23, or whatever this claim is saying, that if I have density and spreadness, then mu A star mu A is very close to 1. Okay, so to summarize, we started out with this wishful thinking. Either I'm close to uniform and I'm done, or I'm far from uniform and I can do induction. Okay, and this led us to the notion of spreadness. If a set A is spread, if no more density increments onto subspaces. Right? I said this is morally the same thing as we did for sunflowers when we said a set family is spread if I cannot go to a link and gain by induction. Okay. And the main thing we need to show is that if you have spreadness, then you get mixing. What does spreadness implies mixing? What is this terminology? You can think of the convolution as taking two pieces and generating something by mixing the two together. Right? I generate x according to mu A, y according to mu A, and I'm mixing the two together by adding them. Right? And what we're saying is if my set is spread, then adding them up gives me something very close to the constant one. Okay? Spreadness implies mixing, meaning once I'm spread, I add up two copies, I mix to the uniform distribution. And finally, so as I said, so far, most of it has been definitions, but the perspective that you only need to show the convolved distribution is close to 1 is definitely conceptually important. Okay, and it's something that we critically exploit in the arguments that come later. So we're exploiting convolution critically in defining this notion of pseudorandom. Okay, so that is spreadness to mixing. Now let me talk about the second ingredient, which we call spectral positivity. but it's essentially a way to convert uh, underestimation errors to overestimation errors. Hopefully you'll see what that means. Okay, so this is what we're trying to show. And you know, the contrapositive of this is to say that if the convolution is not close to 1, then you're not spread. Meaning, if my convolution is not close to 1, then there is a large subspace with more elements than before. Right? So instead of proving this directly, we'll prove the contrapositive. Okay. And you might see that I did some clever cheat here, in that the star convolution became the difference convolution, right? But these are not the same operations, okay? And it's not a bug or a mistake in the proof. You can make it correct. Basically, there's this general sort of decoupling result saying that the star convolution is always closer to the 1 than the difference convolution. Okay? So if this is lower bounded, then so is this. Okay. So why is working with difference convolution nicer? Again, let's go back to our caricature. We have our universe. We have our normalized probability, so that we are always comparing with 1 instead of 1 over the domain size. And this is what mu-a difference convolution mu-a looks like. Okay. It could be all over, but somehow we want to say that if it is not close to 1, something happens for us. And yeah. Which notation, sorry? This one? So that's the difference convolution of 2 distributions, right? Right, so F's a difference convolution g of x is, if I pick a random z, and I look at the inner product f and g, where the difference of the 2 is x. Okay, it's kind of like a convolution, but instead of looking at x plus y, I'm looking at x minus y. Okay, so we have this kind of caricature, and I said intuitively the problematic case is when somehow this curve puts a lot of points in the lower probability region, right? We ideally want to say we are very close to 1, but we are more worried about downward error. Because if I have a lot of points here, then my set 2a could completely lie here and I would miss all 3 apex. Okay, so you're more worried about underestimation errors than overestimation. And usually when I say, okay, show something is close to like the constant 1 function, you might say, okay, I'm going to put a small band around it and say, my curve mostly lies inside this band, right? And along with that, we can also categorize the errors into 2 types. One are upward errors, where my estimate is more than 1, and downward errors, where my estimate is like less than 1, right? And if I think of general densities, there is no correspondence, there is no need to have any correspondence between upward errors and downward. In particular, I can have a function where the upward deviation is completely within the band, but suddenly there are a lot of downward. This is totally possible. There's nothing that rules it out. I could always be like 1.01, 1.01, and then suddenly drop down for a tiny number of elements all the way to 0 or even to 0.1 or something, and then go up. There is no general equivalence we can show between upward and downward errors. Okay? But as it turns out, for a large class of densities, you cannot have such a picture. A large family of densities or probability distributions, which we call spectrally positive, they cannot have only downward errors. Meaning, if you have downward errors, you must also have upward errors. All right? And what does it mean for a density to be spectrally positive? You can think of a density as a function in whatever domain you're looking at, and you can look at its Fourier transform. And the density or a function is spectrally positive if all of its Fourier coefficients are non-negative. Okay, and Fourier coefficients usually are not even real numbers. They can be complex numbers. They can be negative numbers. But here we're saying they have to be non-negative real numbers. Okay. So why is this kind of like a given for us? Where do we get this Fourier coefficients are non-negative? That seems like a very strong condition, right? You have some arbitrary function. I'm saying I want all of its Fourier coefficients to be non-negative. Okay. As it turns out, we get this hypothesis for free because we are looking at convolution. Okay. And once again, if you've done any signal processing course, you'll see that most of signal processing based on this fact that convolution is a much nicer operation in the Fourier domain. If I convolve two densities and compute its Fourier coefficient, then the Fourier coefficients just get multiplied. Okay. So the Fourier coefficient of mu a difference convolution mu a is just the absolute value squared, which is always non-negative, right? So in some sense, because we are looking at the difference convolution already, we get non-negativity for free. If you look at the star convolution, this is not true. What you get is mu a w square, which is a complex number square, need not be non-negative. But if I look at its absolute value squared, then you get non. Okay. So convolution is product of the coefficients in the Fourier domain. So that's why we get the spectral positivity for free. Okay. And the general thing that we show is that if Q is spectrally positive and it is not close to 1, meaning it has some errors from the constant 1, then it must have many points where I'm going up and going above 1.01. Right? Earlier we said if I had general density, I could be very close to 1 all the time, but then suddenly drop down. Spectrally positive ones, you cannot have such a thing. If you're deviating downwards, then you should also deviate upwards. All right. Okay. And how does this work? How do you prove this lemma? You prove it by, actually it has nothing to do with spectral positivity or anything. It's just some statement about a real value random variable. In particular, if I take any real value random variable, which has non-negative centered moments, then you get this inequality. So if I have a real value random variable x, let's say its expectation is 1, then it doesn't mean that expectation of x minus 1 whole cube is non-negative, right? But as long as they're all non-negative, if you're lower bounded for something, then you should also be lower bounded in the actual moment. Okay. But as I said, I'm not going to go into all of the proof steps, but the main ideas. So the main thing here is that if I have spectral positivity, then I can switch between underestimation to overestimation. Okay. So let's summarize. The spectral positivity lemma says that if the difference convolution is not close to 1, meaning the kth norm distance from 1 is at least 0.1, then your kth norm itself is like 1.0. In particular, we have many higher probability elements. Many elements where my value is like 1.0. You might wonder, like, why is this switch from underestimation to overestimation error so important? And it was actually important. Historically, I don't think this has been used in other proofs in this area before. And conceptually, it's very useful because recall what is our goal. Our goal is to say that if I'm not close to uniform, then I want density increment. I want to find a subspace where I have more elements than before, right? Downward deviation just tells me that there is a subspace where I have less elements than before, but that's completely useless for me in terms of induction. It's only when I have an upward deviation can I say that I have more elements than before. Upward deviation means there are these elements which I'm giving more probability to than before, right? Which is what we want. We want density increment. We want to say there are elements which are kind of, there's a region where I have more probability than before. Okay. So that's why the switch is conceptually very important. Any questions about this high level picture? All right. Okay. So that's about spectral positivity. And when we come back, I'll tell you a little bit about how the sifting part, which is the final piece of this jigsaw puzzle. Okay. So let's take a 5-minute break. How was the exam? I had to. You guys did so. You all did so well in the first exam. The median was 30 last time. So I thought, okay, maybe I should make it a little more interesting for you all. So hopefully it was interesting, nevertheless. A couple of those problems are, from my own research. The DNF one, the upper and lower bound, they're actually from a paper that I had in 2012. Literally, the entire paper is basically that. Yeah. No, no. By other sources, I mainly meant like other people. Okay. So I don't want you to go and search for the same exact problem or something, but you can definitely look up any relevant literature. Yeah, yeah. Sure, sure, sure. Or maybe if I don't want you to do that, I'll be more explicit. But it's really hard to enforce that anyways. All right, maybe we can get started. Okay, so let's do this last piece. So where are we, right? So what stage of this entire process are we? So our final goal is to say that if my difference convolution k norm is big, then I can do density increment. meaning I can find a large affine space where my relative density is a constant factor. Okay, so we started with saying mu a difference mu a minus 1 is bigger, but now we kind of took the minus 1 out, okay, which intuitively means that there are many elements which have high probability than they should, and we want to find some structure within these elements. Okay, and so our end goal is to find the full affine space, right? Somehow we need to find a subspace which has high density, right? Subspace is very strong structure, right? Something is a subspace, then when I add it to itself, I stay within the set, right? So a lot of consistency conditions that a subspace must satisfy. Okay. So we're going to relax this problem. Finding density increment onto a subspace seems very difficult, right? Subspace is very, very structured sets. So let me do something seemingly in between, or maybe much closer, much easier. Okay. Let me find increment onto a sum set. What is a sum set? A sum set is just a set which can be written as the sum of two separate sets. I can find a large B such that A intersection B plus B is much bigger than the overall density of A, like 1.05 times W. Okay. Why is this easier than finding a subspace? If I have a subspace, then V plus V is V, right? So when I add two elements in the subspace, I stay within the subspace. That's the definition of a subspace, right? So in some sense, we are saying, okay, let's assume that the most important property of a subspace is that when I add two elements in the subspace, I stay within the subspace. Okay, so that's what this definition is capturing. So if I can find a V, then obviously I find a subset because I can just set V plus V, which is just V, and then I'll get V over there. Okay, so this is definitely a weakening of this requirement. Instead of looking for a subspace, we are going to look for a sum set, something which can be written as a sum of two sets. Okay, and here comes sifting, or you can think of it as the Swiss cheese algorithm. Okay, and if you've seen caricatures before, this is going to be the worst caricature, but of all the things that we're seeing, but hopefully it'll still give you some intuition for the main idea. Okay. So what do we have? So just take a very abstract picture. We have some set S, subset of F3 to the n. And I want to find some sort of meta operation or algorithm which will sift out or identify some structured portion of this set. So ideally, I want to look at like all the elements where mu a star, mu a difference convolution mu a is giving more mass than before, and suddenly say, okay, here's a subspace hidden inside this set. Okay. If I see the set and you ask me to find a subspace, maybe I just do some kind of basis elimination or basis finding or whatever I want algorithm to do it. But I want something as an abstract operation, which doesn't look at the individual element. Okay. So just imagine that this is what my colors are kind of faded out, but hopefully you can still see. So this is my sort of universe, okay? And then I have these circles, these dotted points, which is the set S. And pictorially in the set S, there is a structured portion, which is the square grid, right? Think of that as your subspace. That's my caricature of a subspace. It's a very regular portion where if you add it to itself, somehow it doesn't change as much. Okay, so that's the intuition. So I want some operation on this set S, which will kind of somehow zone in on the structured portion, on the subspace portion than the other elements. Okay, so I want to sift out the structured portion. So the idea that we use is to shift this set and intersect with itself. Okay, what do I mean? You have the set S. I'm going to take a random shift of S in some direction and overlay it on top. Okay, so I call it I said, one way to think about it is the Swiss cheese algorithm, meaning just imagine you have a Swiss cheese slice, which looks exactly like this. The holes represent elements of S, but in the middle, I cut out a grid portion. I cut out a small, tiny square window inside. And then you have a lot of holes around. Okay. Now, what I'm doing is taking the Swiss cheese slice, moving it some random amount, and overlaying it on top of each other. Of course, this is all happening mod arithmetic, so things wrap around. So imagine there's a huge slice, so you don't go too far across. Okay. So I shift this whole pattern, like a cheese slice, a little bit and overlay on top. And I see which elements survive both. Okay. So I look at S intersection S plus S1, which elements are present in both of these things, right? So which holes are kind of, still holes really. I took the slice, I shifted it, laid on top. Some holes will now be covered. Some holes might still survive. Okay. And I keep doing this. I take another random shift, random direction, overlay it on top, and ask, okay, which holes survive once again? Which points are holes in all three of these shifts? Intuitively, what should you expect? These isolated ones should be unlikely to survive. They're the least likely things, right? When you're shifting it out, it's unlikely that they would survive. But somehow, the tiny square window, you might expect that a larger fraction of it will survive. Okay. So again, it doesn't mean to say a big fraction of the square will survive, but relative to the other points, the things in the structure are more likely to survive. And that's all you care about. Maybe the overall numbers are small, but it's relative to the other points. If I'm 10 times more likely than other points to survive, that's all that I want. I want this relative boost. Okay. So a bigger fraction of the inner square will survive than the isolated ones. Okay. So when you do this shifts of the Swiss cheeses, in fact, all of these holes will be covered. But if I put a kind of a nice square in between, there's some chance that this bigger fraction of the square will survive. And that's exactly the algorithm that we use. So to find this sum set, you look at random shifts of the set S and look at all the things which survive across all of these shifts, meaning which elements are in the intersection of all of these things. Right? And here things get quite hairy in terms of doing all the calculations, but I would say sort of the main intuition is that when you do the shift and intersect, you have this qualitative boost. The things in the subspace are more likely to survive. And once you have such a process, you can do the calculations to make it rigorous. Okay. And what is the set S you look at? You look at the set S, which has points of high probability. For the first part, from the spectral positivity part, we know there are many such points. And then we argue that within such points, you can find a sum set which is big. Right? So there is a set B, which is relatively big, and B plus B is almost entirely in S. Right? And how do you do this calculation? In fact, it could have been very messy, but fortunately, it turns out to not be very messy. And there's some beautiful sort of identities that start showing up, which were very surprising to me. I wouldn't have expected that such identities held, but they do. Okay. In particular, if you look at this operation that we're doing, S intersect S plus S1, intersect S plus S2, and so on, it seems like a very crazy operation. Right? If I ask you, okay, what is the size of this set? Even that seems very messy, right? But it turns out that there's an exact closed form expression for what this set looks like. What is the expected size of this set? What is the expected size squared? And all of those things, we have closed form expressions. Okay. So we can calculate them very exactly. Yeah. I would say not. In some sense, we were trying the algorithm before we knew this identity. Okay. Qualitatively, it already seems like it should work, right? If the identities didn't help, maybe the argument would be more messy and more sort of calculations and approximations. But the fact that you can calculate these things exactly is definitely like, big boost. It simplifies things tremendously. Okay. So you can put these things together, you find a sum set, which is to which you have density increment. Okay. But there's still one piece missing, which is that we're only finding a sum set, which is a weaker version of a subspace. Right? We said subspace means that you have all of the additional constraints. Adding any two things stays inside. But this last piece we don't have to do. Someone already did it. This is called almost periodicity. It has many different names or several different names in the literature. But basically, it says that if there is a set B such that B plus B is very close to S, then you can even find a subspace onto which you have density. Okay, going from sum set to subspace is not that it's easy, but it's definitely been done before. So we don't have to do it. Okay. You lose something in the dimension, like if the subspace B had density 2 to the minus L, then the subspace that you find will have codimension L to the 4. Right? So let me summarize kind of the high level picture. So we started out with, okay, so we ended with the sifting part, which tells you that if the difference convolution is very close to, has many high probability elements, then I can find an affine subspace onto which I can do density. Right? So this involves that Swiss-Cheese algorithm combined with this analysis. Then we have the spectral positivity lemma, which tells you that if I'm far from 1, then I must have many high probability elements. Okay, so this hypothesis is needed for that. And then finally, spreadness implies mixing tells you that if A is spread, then you have many 3As. Okay, so there's a notion of spreadness that we define, then spreadness implies mixing, and then SP lemma, and then this. Okay. You need to put all three together, and we get the analytic proof. We get the analytic proof that you work through all the parameters, you get delta roughly 2 to the minus log n to the 1 over 9 suffice. Right. But I said this is all happening over f3 to the n, for which you already saw a better, cleaner argument last class. Okay. But going from finite fields to integers can be done here, but it's quite technical. Even this is technical, but the main difficulty is that over integers, we don't have nice structures like subspaces to do induction. So what really saves us over f3 to the n is we have all of the subspaces to do induction. Over integers, we don't. So what do you do there? You have to work with things which look like subspaces if you squint very hard, and that's what you work with. Okay. And if you use that, you end up with this result that any set which has this much density has many. Okay. All right. So that's the only thing that I wanted to say about this. Here. All right. Okay. We will use Zoom for broadcasting. Okay, so what is this? So the main takeaway from spreadiness implies mixing is you have this additional power, either in the problem or somewhere else, to exploit the mixing operation. You don't need to show that A itself is close to uniform, but you need to show that A convolved with itself is close to uniform. Okay, so meaning use operation. Okay, so that was critical. And then we had the spectral positivity. Right, so which gave us a way to switch from underestimation errors to overestimation errors, right? And then we had the sifting algorithm, okay, which is a way to talk about things. Okay, so let me I'm just looking for one. Okay, so we already talked about number on Fourier model, but we also talked about communication complexity and what randomness gives us power, right? So we have Alice and Bob, they're trying to communicate and compute some function. And then we talked about the equality function, right? Its randomized communication complexity is constant. Deterministic is maximum log of capital. So we talked about the randomized protocol and also deterministic. There's this huge gap between these two things, right? Now we can ask the same question. Does randomness give significant power over communication in the number on four-head model? Okay. We already talked about the number on four-head model and how it can give you non-trivial protocols, right? And understanding that has many, many applications, but even this basic question of randomized versus deterministic for number on four-head is not well understood. Okay. There's one result from about 15 years ago, which showed that there exists a function. By some counting argument, they show that there exists a function whose randomized communication complexity is a constant, but its deterministic communication complexity is log n. Okay, so the maximum possible gap. But for two parties, okay, here's the function. I can tell you here's the equality function for which you have the gap. For number on four-head, we have no such candidate function, at least until very recent. And the best explicit separation that we have was for the checksum function that we talked about in the first lecture, x plus y plus z equals capital N. That we have a separation. Randomized is a constant. Deterministic is triple log n. Okay, so That's the gap that we have, like 3 logs of n versus a constant. Okay. And this is related to the 3 APS question, as we saw. And it's not that we don't have lower bounds for number on forehead. We do have strong lower bounds for the number on forehead model, but all of them somehow are too crude. They can either apply to both randomized and deterministic or neither. Somehow you need a fine-grained tool which can apply to one but not the other, because we want to separate the two complexities. Okay. And so most recently, we kind of solved this problem by giving an explicit function, which is really based off like integer inner product. And randomized communication complexity is a constant. Deterministic is log n to the 1. Okay. Kind of makes progress on this explicit separation question. So the previous one was triple log. Now we have single log to the power 1/3. Okay. So for this, we don't have much flexibility to go into it, but in terms of time. But let me talk about a specific inequality that we proved in our way towards proving the lower bound. Okay, and this inequality might have some applications elsewhere. It also kind of connects to the spreadness versus mixing. Spreadness implies mixing thing that we've been talking about. Okay, so let me ask you a simple question. So I have 3 functions, a, b, and c. So a only depends on y and z, b only depends on x and z, c on x and y. Okay, you can see that there are 3 inputs x, y, z, but each one only depends on some 2. All right. And the question I want to ask is, okay, when is this product of the 3 functions? When can I decouple this product? When is the expectation of a times b times c the same as expectation of a times expectation of b times expectation of c? Okay. Typically, we shouldn't expect this to be the case, right? Because if you think of these random variables, they're no longer independent. They share inputs, so they are dependent. If they were independent, obviously expectation of product of independent functions will be product of the expectation. So the question I'm asking is, are there nice conditions under which I can get something which is like almost, which makes them behave almost as if they are independent? Okay. When can I expect such a thing? And the first thing to notice is that, this can be violated very badly. Consider the following example. So let's say a of y comma z is 1 if and only if y plus z is odd. They're taking 2 integers as input. Output 1 if and only y plus z is odd. B of x comma z is 1 if and only if x plus z is odd. C of x comma y is 1 if and only if x plus y is odd. Okay. Now, the right-hand side, expectation of a times expectation of b times expectation of c is like 1/8. And if you pick 2 random inputs, what is the chance that the sum is odd? Roughly half. Same thing here, so I should get 1/8. Okay. But how about the product of all 3 functions? Can I have a triplet x, y, z? So I said y plus z is odd, x plus z is odd, x plus y is odd? No, right? Because if all of these are odd, when I add them up, I should get an odd number. But when I add them up, it's 2 times x plus y plus z, which is even, right? So they're extremely dependent. The left-hand side is 0. The right-hand side is 1/8. Okay, there's a huge gap, especially when you think of it multiplicatively. So you need some conditions under which, you cannot just hope for this, in very much just based on density or any arguments like that, but you need something more than just density. Okay. So the thing that we showed is that we can in fact decouple this product, the expectation of the products as product of expectations, if the functions a comma b are spread with respect to rectangles. Okay, some similar notion of spreadness. When they are spread and you mix them by multiplying them, what you get is going to be close to the constant one. And what is this notion of spreadness? Conceptually, it's similar. You want to say that, I have my function, which I can think of as a subset of n by n, right? Because, A is a function which takes two inputs and outputs 0 or 1. I can think of it as a subset of n by n. I think of it even as a matrix, okay? Where, I have a 0 if a of y comma z is 0, and 1 if a of y comma z is 1. Spreadness is basically saying that this matrix doesn't look too dense in any one portion of the matrix. Is D spread if for any rectangle, meaning any product set xy, the number of points that you see inside is not much more than the overall density. In the same qualitative definition, instead of having subspaces, we have rectangles. Okay? And the condition that we show is that if I have A and B, which have density roughly 2 to the minus D, and they are D to the 10 spread, you need something slightly stronger, but let's not worry about that. Then their product, AB transpose, A times B transpose of xy, is very close to a constant function. So the role of mixing is now being played by the product of the matrices. So I have two matrices which are individually spread. Neither one is very close to the constant matrix, but once I multiply them, what I get is going to be very close to the constant matrix. Okay? And the proof of this, again, we are going to do spreadness versus mixing, structure versus randomness after matrix products. Earlier, we were looking at convolution as a mixing operation. Now it's a product. Spectral positivity, you had to go from underestimation to overestimation errors, but that comes about from positive semi-definiteness of matrices. There's a notion of sifting, again, which is like the shift and intersect idea, but you have to do it over graphs, and this relates to something called dependent sampling over. Okay? So you put all of them together, you get that inequality. That if A, B, C are spread, then this product is close to the product of the expectation. Okay? All right. And finally, we also have an application of this inequality to a very basic question in graph theory, right? So what is this question? Suppose I give you a graph with capital N vertices, and I ask you, does the graph have a triangle? I guess simple enough. Does the graph have 3 points which are all connected to each other? Okay? How would you do it? What is the simplest algorithm for this? Well, I can just enumerate all possible triples. That takes me cubic time. Right? So the naive algorithm is n cubed, right? I look for all possible triples x, y, z and check if all edges are present. So that's n cubed time, okay? And the fundamental question, which has been around for a long, long time, is there a better algorithm? Is there an algorithm to detect, count, or list triangles in subcubic? Cubic is trivial. Can you do better than cubic? Okay. And it turns out, in fact, we can. There is, you can do it in n to the 2.37 or something. And this comes from fast matrix multiplication, right? Counting triangles is basically like looking at A cubed and looking at the diagonal entries. We have Strasson's algorithm and so on for fast matrix multiplication. So you can get subcubic, which is kind of surprising. Okay. But people have been asking for, like, this is a combinatorial problem, right? So it doesn't have anything to do with matrices or anything, but somehow magically you use all this matrix algebra tricks like subtraction and so on, and you get a fast subcubic algorithm. Is there a combinatorial algorithm which can detect triangles better than subcubic? Okay. Combinatorial means, like, don't use algebra. don't use like subtraction. I think subtraction is the key thing. And there's also a formal definition for this, and there are other reasons to study it also. And there was an algorithm which did better than subcubic, but it barely better than subcubic. Like, it's like n cubed over log n to the power 4 or 6 maybe. Okay, you got some savings by doing some all kinds of tricks, right? Okay, and very recently we gave a substantially more subcubic algorithm. It's like n cubed by 2 to the log n to some power, like 1/7. At least this 2 to the log n should say that it's kind of going to come from the previous thing that we discussed, right? Like the same thing for 3APs and same thing here. Okay, so you get substantially more savings over subcubic algorithm. And what is the connection to this decoupling or communication complexity result? The connection is that triangle counting really looks a lot like number on 4 at communication. Okay, why? So what do we want, right? So if you think of the adjacency matrix as a function which takes 2 inputs and outputs whether or not there is an edge, is it a 0 or a 1? Okay, I have a triangle is a triplet x, y, z such that a of yz, a of xz, a of xvi are all 1. Okay. So imagine I ask you, okay, count the number of triangles. That's the same as saying I want to compute the expectation of a of y comma z times a of x comma z times a of x comma, which looks a lot like the decoupling thing that we just saw. If somehow A is nice enough that you can decouple, then there's no counting to do. I know the answer already. In fact, there are many, many triangles, not just one triangle. There are many, many triangles, right? So we can use the inequality from the Neberon fluid analysis for decoupling dependent products. Okay, so we start with this adjacency matrix. You have your graph. We have the adjacency matrix. We break up the adjacency matrix into pieces so that within each piece or across different pieces, it's easy to look for triangle. Why? In particular, each piece is either spread. If it is spread, I know the triangle's answer because I can decouple the product as product of expectation. Okay? Or it is so small that I can just do brute force enumeration. Right? So in this new regularity lemma, we basically say any graph can be decomposed into few pieces such that each piece is spread or very sparse. And because of this, you can do triangle detection very easily within each piece. And this is what gives you the 2 to the log n to the 1/7 thing. Okay. So that's kind of, the last piece. Yeah, this also makes sense. So, in some sense, I talked about the main ideas underlying the 3AP problem, right? And it had these 3 ingredients: mixing, spectral positivity, and sifting. The same 3 things show up in the application to communication complexity and the decoupling inequality. And the decoupling inequality leads to this fast algorithm for finding triangles. Okay. And one very nice open problem that, I personally have been thinking about, and probably many others too, is find some conditions for decoupling when I have more than 3 functions. Like, we saw something where xy, yz, zx. If they're spread, you can decouple. Besides all the application, this seems like an interesting thing, interesting standalone inequality. But what if I have 4 functions? I have a, b, c, d. What are some nice conditions under which these products, which have crazy dependencies between them, behave as if those dependencies don't exist? Okay. If we have such a thing, then maybe you can even do the last piece. The last piece says that I can decompose anything into regular pieces and I can work with them much nicer. Okay. So let me stop with that today. And when we come back in the next lecture, we'll talk about something else, but hopefully this gives you a good idea of these techniques. Okay. All right. I'll see you all on Monday.